And welcome to this PVTech Tech Talk product series webinar co-hosted with Trina Solar. The title of today's webinar is Inside the Empirical Data Analysis Supporting the Global Adoption of Ultra-High Power PV Modules. My name is Liam Stoker and I'll be your moderator for today's webinar. Today's presentation will last around 1 hour, and within that time we'll have presentations from Trina Solar, the National Testing Institution for Photovoltaic Products at CPVT and TÜV Rheinland. We'll then move on to a roundtable discussion with our panelists today. Shortly, Frank Jiang, Head of Global Product Strategy and Marketing at Trina Solar, will open proceedings before handing over to Dr. Christos Monacrosos, who will then present on behalf of TÜV Rheinland. Dr. Yun Min of CPVT will then present. Before we start though, some housekeeping. Today's webinar will last approximately 1 hour. After our presentations today, there will be a roundtable discussion featuring our panelists, where we'll go into a bit more detail from the presentations. The slides and a recording of today's webinar will also be available shortly after the presentation. But without any further ado, I'll hand over to Frank to begin today's presentations.
Okay, thank you very much, Liam. Let's share my screen. Yeah, hello everyone. This is Frank Jiang from Trina Solar. I'm the head of the Global Strategy and Marketing. Today, my presentation topic is industrialization progress of a 600-watt module progress. Yes. So my presentation will cover below contains. Actually, this year is very special for Trina Solar. It is the 25th anniversary of Trina Solar. Until now, the accumulative PV module shipment of Trina Solar already reached 100 gigawatts. This is a great milestone for us. As all of you know, currently the global installed PV module capacity is about 1,000 gigawatts, which means we have contributed about 10% in the past 25 years. Last year, according to the PVTech ranking data, Trina Solar was ranked as top 2 module supplier last year, and our module shipment is about 25 gigawatts. Trina Solar is always a trustworthy and reliable partner for our customer. We have very good reliability and bankability for our products. We just owned the top performer in the PV year reliability test for 8 consecutive years. Especially our 670-watt modules have achieved top performance in all the PQP sequences. And also, Trina Solar is the only module manufacturer that keeps 100% in Bloomberg bankability survey for 6 consecutive years. This indicated that the global financial market and are confident in the reliability and the system value of our product. And just recently, we have also been awarded AAA rating in the latest PVTech bankability rating report. AAA means the highest grade. This rating system combines both manufacturing and the financial health of the company as well. This chart shows you actually in the past 12 years, the module power development trend. You can see that in 2009, the module power is almost 290 watt, now already increased to 670 watt modules. Trina Solar actually were always a leader of the PV module development. Last year, our Vertex 670 watt modules was launched in March last year, which has been delivered globally now. According to the latest information from European Intersolar last month, you can see that there are more than 10 more companies which exhibited their 600-watt modules. The right-hand side is the major Tier 1 and Tier 2 module manufacturing. You can see almost all of them can provide 600-watt module already. So I think the 600-watt module are becoming mainstream product already now. So what is the value of this 670-watt module? Here we have a brief summarize here. compared to the industry reference 545, you can see that our 670 watt module power increase almost 125 watt. Module efficiency also increased 0.5%. The most important is the stream power increased 32% because we have a lower voltage design. So to verify this benefit and the LCOE and lower down how much it is, so we co-work with Fraunhofer ISA to conduct the value assessment. Left-hand side is a project study in German, monofacial module with fixed tier installation. You can see that compared to this industry reference 540, capex can be reduced about 2.04 euro cent per watt. And the corresponding LCOE can be reduced about 4.1%. The right-hand side is a bifacial module with one portrait system. You can see the capex can be reduced about 0.95 euro cent per watt, and the corresponding LCOE can be reduced 1.9%. So currently, the 670 watt module actually are compatible with the inverter already. You can see here the 200 types from 22 mainstream inverter manufacturers have their solution already, including Huawei, Sungrow, and SMA, Famer, and all the branding already listed here. This Vertex module, 670 watt module, are also fully compatible with tracker already. The 14 top suppliers are compatible with our Vertex module. The branding including Next Tracker, Vertex, and also Trina Solar, and others you can see. Until now, the Vertex module has been widely applied globally. Here is some cases. You can see that not only the utility project, but also CNI rooftop, and Singapore, Spain, and Brazil, and also the Vietnam, and almost cover different scenarios. And here we also have some data until the Vertex module, the shipping record already reached 20 gigawatt already. This page shows you the near future, the 600 watt module, the capacity, how it is we are going on. This data from the third-party PV info link. Left-hand side, this is the cell capacity. Right-hand side is the module capacity. End of this year, the 600 watt module capacity will reach 312 gigawatt, and the cell capacity will reach 295. This means in future, we will have sufficient supply capability of 600 watt module from today onwards. The Trina Solar as the pioneer of 600 watt module, actually we have built up a lot of the manufacturing bases worldwide. By end of this year, we will have a 65 gigawatt module capacity and 50 gigawatt the cell capacity. Our target is to deliver our customer enough 600 watt module worldwide. So finally, I want to give you a brief summary here. The accumulative module shipment of Trina have exceeded 100 gigawatt, and the 600 watt module are become mainstream now. This Vertex 770 watt module can further reduce LCOE about 1.9 to 4% around. This will contribute to the global green energy transition and carbon neutrality, I think. And also this Vertex module, we have excellent capability, reliability, and bankability, which are ready for global application now. I think that's all from my side. Thank you very much. Next, please, Dr. Crystal, it's your turn. Thank you.
Thank you very much, Frank. Christos, the stage is yours.
So my name is Christos Morganocrusos. I'm working for TÜV Rheinland Group, and today I have the pleasure to talk about energy yield service and looking beyond the standard test conditions. So as you may know, the pricing of PV modules is standardly done based on the STC, the standard test conditions. The standard test conditions represent a very strict set of conditions, which irradiance is exactly 1000 watts per square meters, temperature is 25 degrees Celsius, and spectral is AM 1.5. This set of conditions can be easily reproduced in the lab. However, they do not say much about outdoor performance of PV modules, where modules will be exposed to a much broader set of conditions of irradiance and temperature. So at the same time, power plant owners, they sell energy yield. So the topic is very important as it has deep financial consequences. So I would like to take a chance to introduce you to TÜV Rheinland. So TÜV Rheinland, we offer tailor-made solutions for manufacturers, EPCs, and investors along the value chain globally. We have more than 40 years of experience in PV. We perform power plant inspections since 1990. We are active in more than 500 locations in the world that also represent 59 unique countries. We maintain over that 8,000 square meters of lab testing area only for solar. And our global network has over 250 experts worldwide. And now I would like to share with you the agenda that I have for today's talk. First, I want to talk about module power rating against energy yield. Then I will introduce you to the global energy yield measurement of TÜV Rheinland. And last but not least, I would like to talk about the energy yield project which we have together with Trina Solar. So without further ado, I would like to jump to the first part of my talk, module power rating against energy yield. So as I have quickly already introduced, the pricing of PV modules is done based on module power rating at STC. In some cases, there is also some energy yield simulations being done. However, I would say primarily the pricing of the modules on module power rating at STC is deficient to evaluate energy yield performance. The energy yield simulations, they are also good. Of course, in some cases, there is nothing else you can do, but they also come with high measurement uncertainty. The normative basis, which tell you how to perform an energy yield rating, which is not the same as an energy yield simulation, is the series of standard of 61853, parts 1 to 4. In most cases, the first two parts are used for energy yield simulations. So it is very important for the PV industry to realize that we have to start moving away from the watt peak thinking and start shifting our mindset towards energy yield driven decisions. Very often you can find module characteristics which determine PV modules performance outdoors in the dataset of the module. However, these are not always trustable, and the information contained in them has not been necessarily verified by third parties. To conclude, the nominal power rating, which is the watt peak stated on the power on the label, does not tell much about the energy delivery. The energy delivery of a PV module is influenced by various factors, such as electrical properties, module construction, and site-specific conditions related to the installation of PV modules, but also the climatic conditions. Last but not least, bifacial technologies, I would say they bring more attention to the energy yield output of the modules, as they also introduce other factors which were not traditionally taken into account in energy yield simulations, as is, for example, their performance output from the rear phase. So we think that the energy yield monitoring with best available accuracy is needed to study the performance of PV modules under the specific conditions of a certain location. And now I would like to take the chance to introduce you to the global energy yield measurement of TÜV Rheinland. So we maintain 4 sites in the world. First is in Tempe, Arizona. Second is in Cologne in Germany. Third in Tuval, Saudi Arabia. And the 4th location is in Chennai, India. A couple of words about the climate for each location. So the climate in Cologne, Germany is temperate, marine west coast, if you like. The climate in Tuval is subtropical desert, which is also affected by sandstorms. In Chennai is also a hot, humid environment, which is represented as tropical savanna type climate. In Tempe, Arizona, we have a subtropical desert climate. And I would like to share a little bit more information about each site. So modules in Cologne are installed at the 35 degrees tilt, and we have gravel stone underneath, which maybe give some additional yield to perifacial modules. The yearly insolation in Cologne is above 1,200 kilowatt hours per square meters. And there is a very significant part of diffuse irradiance. Basically, it's a cloudy weather, very cloudy weather. So 20% of the irradiance comes from irradiances below 200 watts per square meters. The average temperature is close to 13 degrees. The annual precipitation, there is significant rainfall in Cologne, so it's close to 800 millimeters. And the average relative humidity is 75%. In Tuval, we install modules at 25 degrees tilt. We also have gravel stone underneath. The yearly insolation is close to 2,300 kilowatt hours per square meters. The climate is very sunny, so there is very little part of irradiance which arrives below 200 watts per square meters, just 4%. The average temperature just exceeds 30 degrees. And there is very seldom rainfall there, just 70 millimeters of annual precipitation, with average relative humidity close to 67%. In Chennai, we install modules at a tilt angle of 15 degrees. There is concrete that has higher reflectivity, so bifacial modules may have some additional yield in a concrete terrain. The yearly insolation is also quite high, 2,100 kilowatt hours per square meters. The fraction of irradiance that arrives below 200 watts per square meters is close to 10%. The average temperature just exceeds 30 degrees Celsius. And there is very significant precipitation there, very significant rainfall, which is almost 1,200 millimeters. The average relative humidity is 75%. Last, in Tempe, we install module at 33.5 degrees. There is also gravel stone underneath. The yearly insolation is very high. Arizona is the sunny state, right? So it is close to 2,400 kilowatt hours per square meters. And there is also very small low irradiance, which arrives below 200 watts per square meter, just 5%. Average temperature is close to 25 degrees. Annual precipitation is, we don't expect significant rain in Arizona, right? So it's 200 millimeters, and the average relative humidity 33%. I would like now to take a chance to introduce you to the measurement instrumentation system which we have. What you see here on the picture on the left is a picture of a container which we use to store the electronic loads and the weather station. The container is air conditioned, and this is to minimize influence of the electronic loads by high temperature that could be present in a container. So this is why we have taken the decision to air condition them. We use comparable hardware at each site. PV modules are installed at a shadow-free environment, so we don't expect to have parasitic shadowing there. Modules are installed in an open rack configuration. There is a significant airflow coming below the modules. And we don't expect any artifact from the series resistance of the PV modules, as all modules are connected with a 4-wire configuration. We perform continuous maximum power point tracking and periodical tracing of IV curves. What you see on the picture on the right side, on the top left, you see a picture of a ventilated pyranometer for the measurement of in-plane irradiance. On the top right, you see a picture of integrated sphere of spectroradiometer with optical fiber. So you also collect spectral data. And the bottom left, you see a weather station, which you use to collect wind and information about rain. And on the bottom right, you see a picture of the 2-axis solar tracker, which is used for the measurement of global horizontal irradiance, diffuse horizontal irradiance, and direct normal irradiance. And now I would like to move to the third part of my presentation and talk about the energy yield project of Trina Solar. So first, I would like to give you some information about the test samples. So the test samples are all very high power output modules that have a watt peak exceeding 500 and IEC close to 20 amperes. At certain instances, for example, for bifacial module types, when the irradiance exceeds 1,200 watts per square meters, current exceeds 25 amperes. So before exposing them outdoors, first we characterize the modules in the lab. Before everything, we electrically stabilize the modules, and then we perform an electrical characterization, measuring different irradiances, the performance under different temperatures, the spectral response, and also the angular response. And then we install modules outdoors. We have two sites here, Cologne and TÜV. And each site, we measure their operational efficiency, specific yield, and module performance ratio. So as I have mentioned, modules were installed in two locations, Cologne, Germany, and TÜV in Saudi Arabia. The testing time in Cologne started from November 2021, and it's projected to stop at October 2022. While for TÜV Saudi Arabia, testing started December 2021, and it's projected to finish at November 2022. So as you understand, the project is currently ongoing. Therefore, I'm going to share with you preliminary results. So we have the pleasure to study the performance of 4 different module types, 2 different monofacial module types in Cologne, and 2 different bifacial module types at TÜV. The rated power of the modules in Cologne, the monofacial was 650 watts, while the second monofacial was 535 watts. In TÜV, the first monofacial type, type C, was rated as 640 watts, and type D as 520 watts. The module dimension for type A and type C were 2.3 times 1.3 meters, while for type B and type C was 2.2 times 1.1 meter. The cell width of the cells used in type A and type C was 210 millimeters, while type B and type D had 182 millimeters width. Solar cells made from 182 millimeters width. And now I would like also to bring to your attention 2 different factors. First, that generally type A and type C module had increased low irradiance ratio, so higher low irradiance performance than type B and type D. But specifically for the monofacial module types that were installed in Cologne, low irradiance is very important because the modules were exposed at winter months, so they have received over 40% of the irradiance that they received was below 200 watts per square meters. So the low irradiance performance there is very vital. While for the modules installed in TÜV, there was also a difference in the low irradiance ratio. However, what made the difference in terms of the specific energy yield, which I'll show you later, was the bifaciality. So modules in TÜV, the module type C in TÜV had a bifaciality of close to 70% to 72%, while module D had a slightly worsened bifaciality, 67% to 69%. So the climate that was the climate that the modules were exposed in Cologne had low irradiance and low temperature, while in Tuval, as we expected, it had much higher irradiance and had much higher temperature. So on average, the irradiance in Cologne varied between 770 watts per square meters maximum to 1,150 watts per square meters. While for Tuval, the irradiance was much higher, between 1,200 watts per square meters to 1,300 plus watts per square meters maximum irradiance. The average temperature that we've seen in Cologne was between 7 to 8 degrees Celsius, while for Tuval was much higher, close to 25 degrees. So taking these factors into account, I would like to use the specific energy yield to compare the performance of these modules. So specific energy yield describes the ratio of the module's energy output to the indoor measured power output as standard test conditions, and is calculating by applying the following equation. So it is the sum of the product of the measured power times the time divided by the nominal power. So we can also use the label value here, as we have used in this specific occasion to share with you the preliminary results. So looking at the specific energy yield performance of the module in Cologne, we see that module type A and module type B, they had a difference in performance which was close to 3%. Both modules yielded very high output, but we saw that module type A, that had the larger cell types, that it also had a higher yield. And this can be explained due to the very significant part of low irradiance that were exposed the modules in Cologne, and together with the difference that the modules had in low irradiance performance. We also had two different types in Tuval. These were the bifacial types, type C and type D. Again, we saw that the module that had larger size cells that also yielded a higher output. Here, the differences was somewhat smaller. So we saw higher yield of close to 0.6% in December and January, while the difference in February was 0.1% different. We think that the main reason for these differences is the higher bifacial ratio of the modules. So I would also like to say that there was no significant differences in the operating temperature between different modules. So it is very likely that the bifaciality of one module could explain the majority of the differences in the performance of these two modules. To conclude, we think that the nominal power rating of a PV module does not tell much about the actual energy delivery of the module outdoors. The energy delivery of a module is influenced by various factors such as electrical properties, module construction, and site-specific conditions. The return of PV investment can be significantly increased by considering climatic factors on the energy yield of a module outdoors. The energy yield service provided by TÜV Rheinland provides a complete overview of factors which affect the energy yield of PV modules. Now, Trina Solar's project was studying the performance of 4 different module types, 2 monofacial and 2 bifacial, in Saudi Arabia and Cologne, that represent 2 different distinct climates. We have seen that module type A in Cologne has shown higher energy yield due to its better low irradiance performance than type B, and the high energy yield output of type C than type D in Saudi Arabia could be attributed to its higher bifacial ratio. So with this, I would like to thank you very much for your attention.
Hi, everyone. Now let me introduce outdoor demonstrations for high power module in China, in Yinchuan City. I'm Yun Ming from National Center of Inspection of Solar Photovoltaic Product Quality. My presentation is contains two sections. First, the introduction of Yinchuan outdoor testing-based facilities. Second, analysis of demonstration data for high-power module, especially for the type of 210 cell and 182 cell. First, introduction of Yinchuan outdoor demonstration-based facilities. First, let me introduce my company, CPVT. In 2007, CPVT was approved to establish by state administration for product quality supervision. It's a government department. Now it's named State Administration for Market Regulation of China. In the next year, 2008, CPVT got qualification, accreditation, and acceptance by the SAPQC and was officially put into operation. In that year, we got the CNAS accreditation certification and the CMA certification. CPVT is also the IECE CBTL, belongs to 4 NCB. CPVT is also the first national statutory inspection agency for PV products in China. The mother company of CPVT is Wuxi Institute of Inspection, Testing, and Certificate. We have 4 laboratories in different locations. Our headquarters and main laboratories is located in Wuxi City. Wuxi City is also the origin place of PV industry of China. We have a fire test laboratory in Zhangjiagang City, about 1 hour ride from Wuxi. Our outdoor testing base is located in Yinchuan City, in West North China. This base is covering an area of about 130,000 square meters, including office and laboratories for about 3,000 square meters. This is a picture of buildings, our headquarters. This picture shows the fire lab, and this picture shows the outdoor testing base. We have over 1,000 sets of professional testing equipments. 80% of them are imported from Europe, USA, and Japan. The value of equipment is nearly about RMB 170 million yuan. The pictures shows the chambers, the analysis equipment, the charging, discharging equipment. We have also UAV for testing the IR and ER. CPVT supports the better jobs, cooperate with many famous certificate companies and research institute, for example, TÜV, SGS, CSA, BSI, and from Fraunhofer, Unreal, Suxi, Eurotest, and so on. Now let me introduce the climatic conditions of Yinchuan outdoor testing base. Yinchuan City, located in northeast China. This is north latitude and east longitude. Yinchuan City is both the biggest PV power station place and the wine production base of China. These are the details of climatic conditions of Yinchuan. First, this is class 1st area of solar irradiance. The mean daily exposure is about 18.9 megajoules per square meters. The irradiance time is about 2.5 to 5 hours standard irradiance per day. The spectrum is familiar with AM 1.5. In some months, especially in June and July, the match is up to 95%. The altitude of Yinchuan is about 1,100 meters, not very high. The climate of Yinchuan is dry, heat, high UV, and the high temperature difference. The temperature difference in one day may be up to 25 degrees. In Yinchuan, there may be also the high wind speed in that area. The max wind speed is up to 25 meters per second. It may equal to a force 10 wind. So in Yinchuan City, we can also research the mechanical experience of modules. These are the pictures of our facilities. We have 10 function zones. For example, glass backsheet agent, NMOT testing, model stream agent, system demonstration, and BIPV, and so on. We also have testing bus for power stations. In this bus, we install the simulators, the EL testing equipment, and so on. There are some typical BIPV small systems in our outdoor base. Agriculture PV, lake PV, BIPV, PV tree, and PV plus car charging. Now, this picture shows the spectrum. The red one is the AM curve, is AM 1.5, and the white is the real spectrum. And they are very similar. The date is the last year, 12th July. Now, let me introduce the analysis of demonstration data for high power module. This is a module groups, 3 module types, 210-55 monofacial, bifacial, and 210-66 monofacial. These types compare with the traditional type 182-72 cell, monofacial and bifacial. These two groups is now closed the test. They started to be testing from last year, April. So they have experience about 1 year. The third group is tested the experience time now not up to 1 year, so it's now ongoing. This is test conditions in our base. The on-grid period is from last year, April, and the 2 groups modules is testing period to 1 year. We install the modules in the best angles. The angle of inclination is about 40 degrees. The module lower edge from ground is about 1 meter because there are some grass in our area. So we must provide the edge of module is shadowed by the grass. The ground type is the ground is with sand and small rock. Most is sand. We use string inverter, the capacity of 20 kilowatts for each module string. This is the circuit, the electric circuit of our testing systems. We use a high accuracy voltage and current meters before and after the inverters, because the data from inverters may have high error influenced by the temperatures. These are the pictures of the strings for different type of modules. Now, first we compare the power generation between 210-55 cell type and 182-72 cell type. The blue bar and the yellow bar is normalized power generation of these two type modules, and this blue curve there's a difference of their generation gain. We use percent value. From these curves, we conclude that the average normalized power generation of 210 cell module is 1.7% higher than the 182 cell module. Because this picture shows bifacial modules, so we measurement the reflectivities of our the sand rock land. In most months, the average reflectivity of sand rock is about 15 to 17.8%. Only in February and November, the percentage is lower. It's around 11%. This slide shows power generation compare with from 210-55 cell module to 278-182-72 cell module, monofacial modules. The monofacial the average normalized power generation of 210 modules is about 1.4% higher. It may be a little lower than the bifacial type cell module. We also research the power generation via irradiation. This picture shows their relationships. The left column is the normalized power generation. The right column shows the power generation gain, use percent. The vertical column shows different irradiance sections. When the irradiance is below 800, the power generation of 210 and 182 cell type is about 1.5 to 2.5%. If the irradiation is above the 800 watts per square meters, the power generation of these two type, the difference of power generation of these two type modules is lower. Especially on June last year, the part of irradiation exceed 1,000 watts per square meter is only lower 4%. So most days the irradiance is below the average irradiance is below 800 watts. So we get these conclusions. The total power generation difference of 210 versus 182 depend on the performance with low irradiance. Because in low irradiance, the 210 cell type module can produce more and more powers than the 182 cell type modules. Third, we researched the operating temperature, OT, difference between these two type of modules. The blue curve shows temperature difference with bifacial modules, and the yellow curve shows temperature difference with monofacial modules. The left bar is daily average temperature difference, centi-degrees. So because we measure the backsheet temperature for each stream, so the deviation is about 0.7 degrees because of the wind. The average OT of 210-55 bifacial module is about only 0.4 degrees higher than that of 182-72 bifacial module. And the temperature difference is about 0.3 degrees higher for that monofacial module degrees, module type module. So now let's see the power generation compare with 210-66 cell type versus 182-72 cell type. Because testing period is less than 1 year, so we only show the testing period from November last year to April this year. Now this the abnormal curves because of in this period the equipment measurement is under calibration. The green curve shows the generation gain percentage of these two type of modules. So the normalized power generation of 210-66 monofacial modules is 2.5% higher than that of 182-72 monofacial modules. Last, let me show the summaries of our research. First, the normalized power generation of 210-55 cell module is obviously higher than 182-72 cell module. The gain percentage is about 1.5 for monofacial module and 1.7% for bifacial module. So this performance is equal to our prerequisites. Second, in lower irradiance, with irradiance below 800 watts per square meters, the power generation ratio of 210 and 182 cell type is higher than that in higher irradiance. So this is the main reason why 210 cell module generate more power than 182 cell module. Because in most days in 1 year, the irradiance is below 800 watts per square meters. Our third conclusion is the average operating temperature of 210 cell module is about only 0.74 degrees for bifacial and 0.28 degrees for monofacial. So considering of the outdoor OT measurement deviation is about 0.7 centi-degrees because of wind. The test results shows that there's no influence of power generation caused by OT difference between 210 and 182. So the temperature difference of these two type of modules, then we can ignore them. We may focus more on the cell type of the power generation performance with different irradiance. This is my presentation. Thank you very much. Thank you for your attention.
Excellent. Well, thank you, Dr. Yin, for your presentation, and indeed the rest of our presentations today. We've reached the stage of today's webinar where we can begin today's roundtable discussion, where we'll look to get into a bit more detail around what we've heard. This first question I have, I think, Frank, if you could begin, perhaps, and then feel free, Christos, or indeed Dr. Yin, if you could have any additional insight. We've heard today how it's been reported numerous times that 600 watt plus modules really do derive that better power generation and performance. Could we perhaps have a bit more detail or really understand the impact factors which can demonstrate how these ultra high power modules that are out today do deliver better electricity generation performance?
Okay, thank you, Nim, for your question. I think from the data from TÜV and the CPVT, it shows that we have better power generation. I think the reason, the two factors, is that first one is no irradiance performance, because whenever we got a irradiance less than 1,000 watt per square meters, so we will have the less impact on power generation, because we have a higher how to say that is a high current. So that's why under lower generation we have less impact on our power generation. This is unit reduce. Another one is, I think, shading. I think because our size is 210 millimeters, whenever we have given the same shading size, for example, I think the impact on our module were less than that of 182 modules. I think this is main factor inside. I think, yeah. Thank you.
Excellent, Christos. Have you got any other thoughts on that matter at all?
Yes. So there are many regions that these modules yield higher than traditional types. So first of all, they use larger cells. They can fit more active area per unit area of photovoltaic. They have high efficiency cells, such as heterojunction or topcon being used. They use novel interconnection patterns, like they use shingled or multi-busbars and multi-busbars designs, which can reduce the series resistance and also can have higher resistance to shadowing. They are more resistant to light induced degradation, as they have introduced gallium in the wafer, but also we also see some of these cells, they are N-type, and therefore they are more resistant to LID and LETID. Often these module types, in general, they have also superior temperature behavior. Superior temperature behavior, I do not mean the operating temperature, but I mean the temperature coefficient. So with bandgap tuning, it is possible to reduce or actually increase the temperature coefficient. And these modules, they have higher temperature coefficient for Pmax and VOC. Higher in terms, these temperature coefficients are negative, right? So higher, they're closer, let's say, to 0. They use broader spectral response, which leads to more photons being absorbed, and therefore we have higher ISC, close to 20 ampere, as we have heard. They use novel passivation technologies that could lead to superior low irradiance performance, and also advanced light trapping schemes, which could lead to higher portion of light getting absorbed from oblique angles above 15 degrees. So more or less, these are the reasons that modules today can have better LCOE than modules 10 or 20 years ago.
Excellent. And Frank, I'm going to come to you directly for this question. One of the big impacts that we've seen from this introduction of modules with power outputs of 600 watts and above is the impact on the current and the increase in current. How has Trina looked to optimize the design of the module to cater for that higher current to then produce better generation performance?
Yeah, so basically, I think for this module, we have a lot of innovation inside. So for example, just now, Crystal already mentioned, we have the multi-busbar technology implemented. Also, we have a very dense, high-dense encapsulation to increase the module efficiency. We also have the non-destructive cutting, because now we are using the split cell already. So this means can reduce the micro crack, something like this. We also have very optimization of our frame of the aluminum frame to enhance our reliability, to reduce the micro crack, and also and the wind loading testing, something else. Actually, we have a lot of design and innovative inside. Also, we have we want to mention about the low voltage design. Actually, this is very important to increase the string power of system. So that's why this can reduce a lot of the BOS saving, BOS cost, such like PV cabling, and also the connector, and also raking system. That's why finally we can reduce a lot of the BOS cost to improve the LCOE. This is the reason behind. Thank you. Yeah.
Excellent. Thank you very much, Frank. Ewan, I want to hand over this question to you. We've heard today just two studies, or the results of two studies rather, that are looking to assess this new era of 600 watt plus modules and what they might mean for the sector. But there are an increasing number of studies that really look to put that matter of fact on the record. What do developers or other industry stakeholders need to be mindful of when they look to interpret or read all of that pieces of research? What do they need to really be thinking about?
Okay, I think there are 2 points that the developers maybe need to reinforce. First, that in my presentations, I showed that the reflectivity of our testing areas are only about 15%, because the ground is the ground type is with sand and little rock. But if the power plant is installed in the maybe a lake, sea, and some roofs, the reflectivity may be above to 20 to 25%. So the power generation difference maybe in those type waters or building roofs, the cell type, the 210 type module maybe generate more and more power than the traditional 182 cell module. So the developers must consider the match between the power between the module plant and the inverters. That means especially the bifacial module may generate the higher powers. So this is first. The second, the 210 cell type module, the size may be about, I just simple calculate, maybe about 15 to 30% larger than the traditional module. So the mechanical performance must be considered for the developers, especially when the power plant is located in some typical areas with large wind. For example, the North Europe, Northwest China, and besides the seas and so on. So the stress, the mechanical stress of the glass and the roofs and the some nectars between the module and the some building in other maybe the building roofs or the doors and so on. So the mechanical stress must be considered when install the modules and use them.
Excellent. Well, thank you very much, Yun. I'm going to look to close off this with a quick question to Christos. I think we've heard a lot again around the studies that we've seen today. I want to look slightly into the future for this one. How might some of these conclusions change, Christos, when with these panel outputs that we're talking about? Industry is already looking at 700 watts and above. There's new cell module technologies, cell structures coming out. How might some of those conclusions change when new technologies come into the fore, whether it is TOPCon, heterojunction, indeed tandem in the future? What might we look to see?
Indeed. So as we increase significantly the module power, there should be some contributions. So one contribution comes from the cells. Either you have to innovate using novel technologies, or you have to increase the cell area, but also you have to consider also the interconnections between cells. So today we see multi-busbars configurations being used. There are also different things which you can do in terms of light-induced degradation, that these cells are showing being more stable over time. So as I have mentioned before, things like gallium being introduced in the wafer, also N-type, which is inherently resistant to LID. These technologies are being used. We also see modules having better low irradiance performance than 20 years before. This can be explained by the maturity of passivation technologies that have been researched. We see that PERC modules, for example, when they were introduced, they contributed significantly into further lowering LCOE. And we think also in the future that AJT technologies, TOPCon, will do the same.
Excellent. Well, unfortunately, that is all we have time for today. Of course, another reminder that the presentations and the recording from today's webinar will be available to you shortly, so keep an eye on your inbox and indeed on PV Tech for those. A huge thank you to Trina Solar for supporting the webinar today, to Frank, to you, and to Christos for presenting, and indeed all of you for your attention today. Thanks again, and we hope to see you next time.
Thank you so much.
Thank you very much.
So much. Thank you.